Swayam Prabha. Digital India. Educated India.
Well, so before going to the choked flow condition for homogeneous flow, there is one particular question. So, I would like to clarify it, that instead of a converging nozzle, if we have a converging diverging sort of a nozzle. Okay. So, under that condition what happens? Now, let us see again, we have that tank, and from that particular tank if we have something of this sort. Okay. So, here we know that the conditions are stagnation conditions. Okay. P 0, T 0, rho 0. Here it is again this is connected to this. Actually, I did not have plans to teach this, but I do not know whether it is going to get little more complex or not. So, this is just the same particular situation which was there, but there we had a converging nozzle, here we have a converging diverging type of a nozzle. Okay. Now, here the upstream conditions are maintained. This is known as the exit pressure and this is known as the back pressure. Now, so we find that the nozzle, it discharges to this particular back pressure. Now, initially what initially again the valve is closed, everywhere the pressure is P 0 and there is no flow, just like what we had seen in the previous case. Here also I would like to plot your say P by P 0 with distance across nozzle, same thing. So, initially it is 1.0, here we do not have any particular flow. Now, what we do? We keep on reducing P b, fine. We keep on reducing P b, as we reduce P b, P e equals to P b and flow starts. Okay. So, therefore, we find that it is something of this sort. Okay. It keeps on, we keep on reducing P b, P equals to P b and we get a flow something of this sort. Okay. This goes on till we reach say M a equals to 1.0. Okay. So, after that what we find is that we keep on lowering P b in such a way that finally we get sonic conditions at the throat. So, we get it something of this sort, and then moment we get sonic condition at the throat, the flow rate is maximum here, just like it was in the previous case. Moment we have sonic condition at the throat, then supersonic conditions here. So, under this particular condition the flow rate is maximum. Okay. For this particular given nozzle, for this particular stagnation conditions, we find that we cannot reduce rather we cannot increase the flow rate any further. Now, if we keep on reducing the pressure slightly more, okay, so we try to reduce back pressure more. Now, then what happens? Upstream the flow is not affected. Okay. Upstream the flow remains the same, it does not respond. But in this diverging section what happens is flow initially it becomes supersonic sort of a thing, and then it tries to adjust itself by a series of shock waves, the normal shock which are standing inside the nozzle. I would not like to go into the details of shock waves etc., because compressible flow is not my topic is multiphase flow. I just wanted to teach a little amount of this, so that some portion rather you have some idea of compressible flows and you can correlate it when we come across that. Okay. So, the point is what happens initially when we initially there is no flow, when P b is closed, everywhere the pressure is constant. Gradually we open it, as we open it P b reduces, when P b reduces P e also reduces, but P e equals to P b, and so P is also controlled by this particular valve, and as this happens we obtain the graph which we had obtained in the previous case. Okay. Now, this keeps on continuing till we get the maximum particular flow rate at m a equals to 1. Okay. This is the maximum for the given stagnation conditions and the given nozzle design. Okay. Now, if we reduce the back pressure further, then we find that the flow upstream of the throat that does not respond at all, but in the downstream section or the diverging section, the flow it initially becomes supersonic and then it adjusts itself to the back pressure P b, because finally it has to come to this pressure P b. Okay. So, therefore, then it adjusts itself to the back pressure P b by means of shock waves, and in this cases we find that the position of the shock it moves downstream as P b is decreased. As we keep on reducing P b, we find that the upstream pressure it does not change, but the downstream pressure lot of shock waves etcetera they come, these shock waves they are initially standing and then they gradually propagate downstream. And so, in this particular cases the position of the shock it moves downstream as P b is decreased, and finally, normal shock we find they stand right at the exit plane, and the flow in this particular section it is now supersonic, and after that we cannot adjust it any further. Okay. So, therefore, the same thing happens, but in this particular case we can go from the subsonic to the supersonic zone, but that too also till a particular point when choked flow conditions has reached here. Moment choked flow conditions has reached in the neck region, we cannot do anything more, although the flow in the upstream region is not affected, but in the downstream region we find normal shocks are there and these shocks they start propagating and the flow rate cannot be increased any further. Okay. So, if you see these particular cases here, the condition it's something like in this particular way these shock waves they are generated and this normal shock waves they are propagated here, and in this then gradually oblique shocks they start and so on and so forth. So, that goes into the area of shock waves. So, this was all that I had to tell you about compressible flows. Okay. Now, our main idea about teaching you all these things they started just because we had a denominator, if you remember, in the homogeneous flow situation. Okay. We had this for the homogeneous flow situation, if you see we had this particular denominator, just a minute let me we had this particular denominator and we tried to find out that for this particular denominator it signifies. Now, if you remember in our introduction chapter, when we were doing the introduction, what I had tried to do, I had tried to deduce the continuity and the momentum equation for incompressible flows. This was the situation. For incompressible flows, I had tried to deduce it and this was the case. And then I told you that for compressible flows what happens, this in this particular case your rho g u is a variable phi because rho varies, and since rho varies with z, so therefore, accordingly the acceleration pressure drop it takes some different forms and finally, we had come to this particular denominator. Now, if you notice this particular denominator, let us see for this denominator, I have it is already done, but I would like to do and explain this further to you. This was the denominator for compressible flows. Fine. Now, what is G equals to? We know G equals to rho u, that we already know, is not it? Or G square equals to rho square u square. Fine. And what is this dV dP equals to? This is nothing but equal to 1 by rho square d rho dP, agreed, or this is nothing but equal to, Can we write it in this particular form? And what is this equal to? dp d rho a square, right. So, therefore, this is nothing but minus 1 by rho square a square. You agree with me? So, therefore, your 1 plus g square dv dp, this is nothing but equal to 1 plus rho square u square by minus rho square a square, right. Or in other words, we find the denominator, which I had already told you that we will be discussing the significance of the denominator later. This is nothing but, or this is 1 minus, is not it? So, therefore, what do we find? We find that the denominator in this particular case, this gives you an idea about the condition where Ma equals to 1, or this gives you an idea about the choked flow condition. So, therefore, the denominator for single phase compressible flows, this corresponds to the choked flow condition, or Ma equals to 1. Now, we find that if we look at the denominator which we had obtained for your this particular case, for the homogeneous case. What was the denominator that we had obtained for the homogeneous case? Let us see now. That was 1 plus g square 2 phase x dv 2 dp plus 1 minus x. This was the denominator which we had obtained. Okay. Now, the point is, so if the denominator under that condition had corresponded to choked flow condition, then in this particular case also, this denominator should also correspond to a Mach number of two phase flow under homogeneous flow conditions. Do you agree with me? Isn't it? We have, it is just simply fluid flow. We have simply done what we had done for the compressible flow case. Agreed? What extra have we done? We have taken into account certain averaged parameters or average properties, and instead of G rho we have G Tp, rho Tp, and so on and so forth, and we have a mass fraction quality here. But the same approach was used. We have used the continuity equation, we have used the momentum equation, and we have considered the acceleration pressure drop due to the density changes of the fluid. Usually one fluid is compressible, the other is not, but to keep matters generalized, we have considered compressibility of both the phases. Finally, we have arrived at a denominator which is of the same form that we had obtained for the compressible fluid flow cases. So, therefore, if this corresponds to 1 minus Ma square for single phase compressible flow, this must correspond to 1 minus Ma square for two phase homogeneous flow, is not it? So, therefore, just like we know that the Mach number for compressible flow is equal to U by A, in this particular case, this particular Mach number for two phase, this should have a form of UTP by A or ATP. Fine. There one thing you remember, there we found that velocity of sound A, it was a constant. It depends upon that particular material. For air it is one particular value, for water it is one particular value. So, A is a constant. We do not know in this homogeneous particular case what is going to be ATP, but definitely ATP must correspond to the velocity of sound in this two phase flow under homogeneous flow conditions under the present circumstances, is not it? Under this particular pressure, temperature, composition, etc., etc., the speed with which sound will be propagating in this two phase flow medium under homogeneous flow condition, that should correspond to ATP. This part all of you agree with me. Okay. Now, let us see what is the expression of ATP here. is it a constant like single phase flow, or does it depend on any other parameter, and if it depends on any other parameter, what are the parameters, how to evaluate, how to estimate, or rather how to quantify ATP in terms of known measurable parameters, right. So, therefore, what do we find in this particular case? We find that in this particular case, if this expression has to be equal to mTp, this has to be equal to 1 minus UTP square by ATP square, agreed. Okay. Or in other words, we find UTP square by ATP square, this should be equal to minus G square Tp, which is again rho Tp square UTP square into x dV2 dP plus 1 minus x dV1 dP. This is acceptable. Again we can cancel the two, so that we can get ATP in terms of certain measurable things. Okay. So, what do we get? We get in this particular case then we get here 1 ATP square, and this should be equal to 1 by rho Tp square x dV2 dP plus 1 minus x dV1 dP. We should get something of this sort, agreed. Now, what about these terms, this dV2 dP and dV1 dP? We have already derived dV dP, same form this should come. So, therefore, these should signify the velocity or the acoustic velocity in fluid 1 and fluid 2 under this pseudo homogeneous conditions. That means, instead of this two phase flow, if fluid 1 would have been flowing under the same conditions of two phase flow, same conditions of temperature, pressure, etc., then the velocity of sound which would have been there is represented by dP d rho 1 in this particular case and dP d rho 2 for fluid 2, agreed. So, therefore, how can we define these particular things? This dV2 dP, this is nothing but equal to minus 1 by rho 2 A2 square, fine, and dV1 dP is nothing but minus rho 1 A1 square, where this A2 and A1 are the acoustic velocities in fluid 2 and fluid 1 under this pseudo homogeneous conditions or under the conditions of this homogeneous flow, fine. So, therefore, from here we get that instead of what we had written it down here, here. So, in place of dV1 dP and dV2 dP, we can substitute these particular terms. Yes. Now, let us substitute them and let us find what we get. If we substitute, we get ATP square, this is equal to 1 by rho Tp, let us take one rho Tp inside, and we get alpha rho 2 by, how do we get it? I am going to tell you. What have I done? Achha, let me do one thing, this will not be easy for you. Let me simply take one rho Tp here. I can write it in this particular form. Yes or no, you first tell me. Okay. I have just substituted dV2 dP and dV1 dP in terms of these two parameters. This I have already derived just now, and on substituting them we find that instead of dV2 dP I have written rho 2 A2 square, instead of dV1 dP I have written rho 1 A1 square, and here I have just taken one rho Tp inside. So, it is x rho Tp and this is 1 minus x rho Tp. Till this much I hope you do not have any problems. Now, if you remember, I had derived one particular expression. If you remember that expression, x rho T p equals to alpha rho 2. How did I get that? What did I tell you? That rho T p is the weight of, say, 1 unit volume of two-phase mixture. Fine. So, therefore, kg of two-phase mixture in, say, 1 liter two-phase mixture. What is x rho T p? It is the amount of phase 2 in this particular 1 kg mixture. Try to think and tell me. What is x into rho T p? Rho T p is the total weight of unit volume. Suppose I have 1 liter or 1 meter cube of mixture, then what is the total weight of this 1 liter mixture? It is rho T p. Fine. Now, in this 1 liter mixture, the weight is rho T p. What is the weight of phase 2 here? It is naturally the mass fraction of this rho T p kg, which comprises of phase 2. Clear to all of you? Therefore, if the total mass of the two phase mixture is rho T p kgs, then the mass of phase 2 is x into rho T p kgs, where x is the mass fraction of phase 2 in this particular amount. Fine. So, therefore, amount of phase 2 in unit volume of mixture is the total weight of the mixture and the mass fraction of it which is there. Now, you see on this reverse. Now, in this particular unit volume, okay, in this particular unit volume, what is the volume of phase 2? Alpha. Think and say, what is the total volume of phase 2 in unit volume of the mixture? It is the volume fraction of phase 2 in the mixture. X is mass fraction, alpha is volume fraction. Agreed? So, therefore, the volume of phase 2 in unit volume of mixture, this is equals to alpha cc liter, whatever it is. What is the weight of this alpha meter cube or alpha liter of phase 2? The weight or mass, let me write, mass of phase 2 in unit volume of mixture. Okay. In unit volume of mixture, the volume of phase 2 is alpha. What will be the mass of this alpha? Alpha into rho 2. So, therefore, we find that mass of phase 2 in unit volume of mixture is alpha rho 2, and this is the mass of phase 2 in unit volume of mixture is also x into rho T p. Correct? So, therefore, we find x rho T p has to be equal to alpha into rho 2. Do you get my point? Because both of these x rho T p and alpha rho 2, both of this, they signify mass of phase 2 in unit volume of mixture. This particular relation is very, very important. It will help you to solve several problems. So, these are equal and they are equal to mass of phase 2 in unit volume of mixture. So, I can deduce this particular relationship. Same way, I can also write down 1 minus x rho T p equals to 1 minus alpha rho 1, where this signifies mass of phase 1 in can I do this? So, therefore, these are the two relationships that I have deduced, and these two relationships are very, very important. Right? Now, let us look at the ATP square, the two phase your acoustic velocity, this particular expression. What was the expression? It was rho Tp square x by rho 2 A2 square plus 1 minus x by rho 1 A1 square. This was the expression which I had obtained. Probably there should have been a minus sign, oh no, minus has cancelled out. So, this is the expression. Now, if I take 1 rho T p inside, then what do I get? Rho T p into x, and that is nothing but equal to alpha into rho 2, fine. So, therefore, I take 1 rho T p inside and then I get 1 by rho T p alpha rho 2 A2 square. Again, instead of 1 minus x rho T p, I can write 1 minus alpha rho 1 by rho 1 A1 square. Can I do this? Yes. So, these cancels out and this cancels out, and I can this rho T p also I can simply write it down as alpha rho 2 plus 1 minus alpha rho 1. Why am I doing all these things? So that I can express two phase acoustic velocity in terms of certain known parameters and in terms of the minimum possible number of known parameters. So, just for that reason I am trying to do this entire endeavor. Agreed? So, therefore, I can substitute this particular rho T p in terms of alpha rho 2 plus 1 minus alpha rho 1. Let me do it and let me see what do I get. So, therefore, I get say 1 by A T p square, that is alpha rho 2 plus 1 minus alpha rho 1 into alpha by rho 2 A2 square. Sorry, there was squares here. Where is Acha, just a minute, there were squares here. Okay. So, did I make any more mistakes anywhere? Let me see. Here also there should have been squares. Please correct these things. These were all squares. Okay, just correct these things. They should have been squares. I missed out them. Yeah, they are all squares. I had missed this out. Anyhow, so therefore, just correct all of these are squares. Okay, I had already deduced them, I believe, when I had, see here itself I had deduced rho square, rho square. Okay. So, this was the thing, dv dp equals to minus 1 by rho square a square. Okay. So, from there it had emanated. So, therefore, I find that ATP square equals to alpha rho 2 A2 square plus 1 minus alpha rho 1 A1 square. Okay. So, this is the expression which I have obtained. So, what do I see from this expression? We see rho 1, rho 2 they are constant. So, ATP it is definitely a function of alpha only, isn't it? So, for any homogeneous two phase mixture, this is just for homogeneous flow conditions only, for nothing else. ATP is a function of alpha only, isn't it? So, therefore, if we change alpha under homogeneous flow condition, my two phase sound velocity is going to change, number 1. Number 2, this shows that unlike single phase flow, your acoustic velocity for two phase flow condition is not a constant, it is a function of composition. This is very important. For single phase flow, it was a constant characteristic of that particular medium. In this particular case, it is not a characteristic, it is not a constant characteristic of that particular medium. It depends upon the acoustic velocities of single phase flows, but along with that it also depends upon the composition of the two phase flows. Now, if it depends upon the composition of the two phase flow, then definitely with composition ATP should change, or the two phase acoustic velocity should change, and there definitely must be one particular value of alpha for which ATP will be a maximum or a minimum. Do you agree? Isn't it? So, therefore, we can actually manipulate, or we can actually control ATP, or we can actually modify, or we can have a control over ATP just by adjusting the compositions of the two phases constituting the two phase flow, isn't it? And how to get that particular optimum value of alpha? Definitely for that particular optimum value of alpha, dATP d alpha has to be equal to 0, isn't it? Now, let us observe this particular equation. Now, in this particular equation, just note that usually it is a gas liquid or a vapor liquid mixture, rho 1 has to be much greater than rho 2. Do you agree with me? And rho 1 A1 square has to be much greater than rho 2 A2 square. So, if that is the case, then this particular term it disappears off, isn't it, because rho 1 is much greater than rho 2. You agree? And this particular term should also disappear off, because since this is much greater than this. So, therefore, usually we find that 1 by ATP square for air water mixtures, this is not for anything else, just for air water or vapor liquid mixtures only we get this. What do we get? 1 by ATP square, then this is nothing but equal to 1 minus alpha rho 1 into alpha by rho 2 A2 square, isn't it? So, rearranging and writing, we get alpha into 1 minus alpha rho 1, I think, yeah, rho 1 by rho 2 A2 square. Fine. Now, this is a function of alpha. Okay. Since this is a function of alpha, therefore, what do we get? That ATP square, this is equal to rho 2 A2 square by alpha into 1 minus alpha into rho 1. Fine. And what is d alpha, d ATP square d alpha? Now, this we know, this will be equal to, just simply if we differentiate it, we get rho 2 A2 square by rho 1. You can perform the differentiation and you can find for yourself, it is just d alpha of 1 by alpha into 1 minus alpha, because A2, rho 1, rho 2, all of those they are constants. So, therefore, this gives us rho 2 A2 square by rho 1 minus 1 minus 2 alpha by alpha minus alpha square whole square. Fine. You can, you see these different, whatever I am doing, I am just doing it, you are copying it down. Please remember, you have to perform these differentiations on your own, these computations on your own, so that you can perform them in the exams. This is a must. Okay. So, therefore, if I have d alpha of ATP square equals to 0, for this particular case, what do I need? This can be equal to 0 only when this term equals 0. Agreed? Or in other words, 1 minus 2 alpha equals to 0. And what does it give you? Alpha equals to 0.5. So, from this, what do we get? We find out that for two phase homogeneous flow, acoustic velocity is maximum at alpha equals to 0.5. So, therefore, acoustic velocity is not constant under these conditions, it is a variable and it is a function of alpha. Interestingly, we find that for 50% void fraction, For air water system, remember we have made several approximations. Number 1 is air water system, otherwise, or vapor liquid system, otherwise we cannot write rho 1 is much greater than rho 2, rho 1 A1 is A1 square is much greater than rho 2 A2 square. This was the first approximation we had made. If you remember, we had from this particular expression we had reduced to this, and then finally from this expression we obtained this particular expression. So, first thing is this rho 1 A1 square is much greater than rho 2 A2 square, rho 1 is much greater than rho 2. So, this is number 1, for air, water or vapor liquid. Then next is homogeneous flow condition, otherwise we could not have replaced rho Tp with alpha alpha rho 2 plus 1 minus alpha rho 1. This we could do for homogeneous flow condition. In fact, under that condition alpha equals to beta, which becomes a input parameter. Okay. So, therefore, we find that for homogeneous two phase flow of vapor liquid or gas liquid mixtures, we find that your the maximum acoustic velocity is obtained for a Voigt fraction of 0.5. Okay. So, this completes our discussions of the homogeneous flow theory, and in the next class we are going to start the drift flux model. Okay. But before that, I had just wanted to discuss, I will be giving you tutorial sheets and you will be solving them out on your introduction part on the homogeneous flow model and so on and so forth. But before that, I just wanted to discuss one or two problems, so that we can see that when we make some sort of simplifying assumptions, then under that condition maybe analytical solutions are possible, much simplified solutions are possible. So, just I would like to discuss one or two problems, so that you can do them as your home assignment and find out the results. So, those problems if I discuss, let me see whether I have those problems or not. So, I would like to discuss these problems. Just let me see, yeah, it is there. So, suppose we have water which is flowing through a pipe, say at a particular velocity, okay, under saturated flow conditions. Okay. So, suppose we have a condition something of this sort, we have a vertical pipe through which water is flowing, okay, and initially it is water at saturated conditions. So, here we are having x equal to 0, okay, and then gradually as it flows we have a constant heat flux, say phi, and so gradually this water it starts vaporizing and we have a vapor liquid mixture inside this. Okay. So, I would like you to find out the pressure gradient delta P over a length L, okay, delta P over a length L for linear change of x with L. Is my question clear to you? My question is that we have a vertical pipe, okay, vertical pipe implying that more or less all your gravitational force, frictional forces, acceleration forces, all of them are there, agreed. And in that particular vertical pipe I have introduced water under saturated conditions. That means x equal to 0, but moment it enters, since there is a constant heat flux. So, under this condition some amount of vaporization starts, and as we go up the quality of the mixture it increases, and gradually we get a higher and higher quality of vapor liquid mixture. Now, over a particular length L, I would like you to find the pressure drop when we assume that the change of quality with length is linear. Can you tell me under what conditions we will have a linear change of quality with length, and how do we signify or how do we quantify a linear change of quality with length? Very good. We denote it as dx dz equals to constant, and this happens for constant heat flux conditions, isn't it? When the heat flux is constant, the area is constant, etc. Under those conditions we have dx dz equals to linear. Now, how to proceed? Now, naturally my starting equation should be, from here I should obtain the frictional pressure gradient, okay, and from here the acceleration pressure gradient can be obtained, and the gravitational pressure gradient, from here the gravitational pressure gradient can be obtained. If I add all the three, then I should get the total pressure gradient. Once I integrate it over length, I should get the total pressure drop, right. Now, notice certain things, we find that for the acceleration pressure gradient, in this particular case, it can change due to a change in density, it can change due to a change in area. In our case, we do not consider the change in area at all, it is a vertical circular pipe. So, this particular term is no longer there. We have this particular term, we have the gravitational term, and we have this particular term, where it is already specified in the problem that dx dz equals to constant. Okay. So, therefore, for this particular case, if we write down the different terms, then what do we get? In fact, I will give you certain values so that you can work out the problem. Say for example, in this particular case, the water at saturated conditions, the G, let me put it as 300 kg per hour meter square, so that you can actually put values and you can work it out. Say it is entering into a pipe of say 2.5 centimeters diameter, and the length is 2.0 meters, or we can put it 1.5 centimeters diameter, it is 2 meters length, and the water is flowing at 300 kg per hour meter square. And in fact, I have already told you dx dz equals to constant, and therefore, it implies a constant heat flux. Okay. See, the constant heat flux, if I give you the value, then in that case what you can do, you can find out the dx dz equal to constant, this particular constant value you can find it out, isn't it. So, therefore, the heat flux you can take it down as 2 into 10 to the power 5, oh chai, this is in BTU, I forgot to convert it. Anyhow, I think I do not have the converted value anyhow. So, therefore, this I have it, sorry. So, therefore, this is at 100 kilowatt power, you do not take this, you take it as 100 kilowatt power. Okay. So, therefore, this is a 1.5 centimeters pipe, this is a make it 2.5 meters length, and it is being uniformly heated with a 100 kilowatt power, and this flow rate I have already given you as 300 kg per hour meter square. So, you are required to calculate the total pressure drop over a length of 2.5 meters, and then the measured value, let me tell you, people have measured and they have found out the measured value as say 10 psia. So, you are supposed to compare with this measured value, definitely you will not get a very good comparison. So, you have to comment on why you have not got a very good comparison. Okay, why I have given you these values? I have given you these values just for so that you can perform the complete derivation, and then you can substitute these values and we can actually work out the problem. Okay. Now, since I have given you the total pressure under which, have I given you the total pressure under which it is operating? You just take up the pressure under which it is operating is saturated water, it enters at 400 psia. Okay. So, inlet conditions are 300 kg per hour meter square of water entering at saturated conditions at 400 psia in a tube which is 1.5 centimeters in diameter and 2.5 meters long. It is uniformly heated with 100 kilowatt power, and the saturated water enters the base at 400 psia, and we are supposed to calculate the total pressure drop and compare with the measured value of 10 psia. Agreed? Now, in this particular case, how do we proceed? Firstly, since it is water, you can refer to steam tables and you can find out all the properties under the inlet conditions. So, you can find out the specific volume V1, you can find out V2, you can find out H12, you can find out V12 and so on and so forth. Okay. Now, what about the different expressions of pressure gradient that we have? The frictional pressure gradient, the acceleration pressure gradient, as well as the gravitational pressure gradient. So, in this particular case, say suppose we mention dP dz frictional. So, this can be obtained as just like we had obtained it in this particular case, this can be obtained from the expression which is written down here. So, it is 2 f T p g square by d V 1 plus x V 1 2, is not it? So, from this we can obtain the your frictional pressure gradient. What about your gravitational pressure gradient? This is simply G L by V, or rather sorry, G d z, very sorry, G d z by V 1 plus x V 1 2, is not it, rho G d z. And what about your acceleration pressure gradient? Your acceleration pressure gradient, you can obtain it as G square V 1 2 dx dz, where you know that this particular dx dz is linear, which I have already mentioned. Fine. So, you know that more or less everything you know except FTP. Several students were having problems with FTP. So, how to define FTP? More or less in this particular case, what you can do is you can find out the Reynolds number, and you will find that the Reynolds number is very high. So, for that particular case, and one more thing, since here water is entering at saturated condition and flowing up. So, for this particular case we can find out RE liquid only, and then we can more or less assume, because at the entry condition it is just liquid, okay, and based on this ReLO we can find out the FTP. We will usually, for the condition that I have given, your ReLO will lie under the turbulent flow conditions. When nothing is given, simply assume FTP to have a constant value of 0.005, just to make matters simpler for you. Agreed? When nothing, if something is specified, then it is fine. When nothing is specified, then you can simply assume FTP equals to 0.005. So, moment you know this, you know V1, you know V12. So, therefore, more or less you can find out the gradient, the frictional pressure gradient. Okay. Similarly, the gravitational pressure gradient also you can find it out, and the acceleration pressure gradient also you can find it out. Now, how to find out the pressure drop from the pressure gradient? That also you know very well. Your delta P is nothing but equal to minus integral 0 to z dP dz into dz. So, therefore, dP dz, by adding all these three you can find out dP dz, and then if you integrate them with respect to z, you can find out delta P. Agreed? And you find that the only variable in this particular case, the thing which varies with z, is just x, nothing else varies with z. Okay. If you see the expression, you find that g square V1, V12, nothing else varies with z, only your x varies with z, and dx dz equals to it is linear, therefore, dx dz equals to a constant c. You can find out the c from heat balance equations. Okay. And so, therefore, if you substitute these and if you perform this particular integration, more or less the expression which you are supposed to expect is 2 FTP. You please do it and you see whether you have got it or not. The final expression which you are expected is something of this sort, V12 by V1 into x plus GL by V12 x ln, write it down here, 1 plus x V12 by V1. Just see whether you get this particular expression or not. Okay. So, this is your home assignment, do it and let us see whether you get it or not. Okay. So, therefore, this completes our homogeneous flow theory, and if we have certain simplifying assumption, then the situation becomes simpler. Accordingly, we can proceed. We will be doing a few more problems, so that the situation becomes much more clear to you. Okay. Thank you very much.